Okay, hello everyone. Welcome to 130B, Quantum Mechanics. So we are going to start our lecture today. So today we are going to continue our discussion about observables and measurements. So let me first recap what we have learned last time about physical observables. We have learned two important postulates in quantum mechanics, all regarding observations and measurements. Postulate number 2 is saying that every physical observable in the quantum system is represented by a Hermitian operator. And then remember that every state is a ket vector. And then as a Hermitian operator, we know that it has spectral decomposition, meaning that it has a set of eigenvalues and a set of corresponding eigenvectors. Both are very important in understanding the measurement process. So the eigenvalues will correspond to all the possible measurement outcomes. When you measure this observable, you're not going to observe anything other than the eigenvalue. Once you observe one particular eigenvalue as the outcome, then you know that the system will collapse. The state will be updated to a new state. The new state will be the eigenstate correspond to that eigenvalue. However, sometimes the eigenstates can be degenerated, meaning that there are several eigenstates correspond to the same eigenvalue. Then it's a little bit more tedious down there that we have to use projection operators, ideas like that. So this is actually what postulate number 3 is talking about, given a quantum system in a state psi, and then if you try to observe O, and then the probability to observe this particular outcome, OK, which is the eigenvalue of this O operator, is given by the overlap of the corresponding eigenstate with the original state. And then this is the fidelity between these two states. And this follows from the Born's rule. And if this OK is observed, then the state will collapse to this eigenstate. So that's the process. However, when there's degeneracy, we also said that, OK, then you have to be more careful. And then this is a more careful analysis that there are multiple, basically, n states which correspond to the same eigenvalue, OK, of this O operator. Then the probability basically is to aggregate the overlap of your original states with each one of the degenerate eigenstates in this degenerate subspace. So that is the total probability for you to observe that particular eigenvalue OK, because there are multiple ways of realizing that, so you have to sum the probability together. And after observing this eigenvalue, and the state will again collapse. But now it doesn't collapse to any particular state, but instead it could collapse to a superposition of all these degenerate eigenstates. And the superposition coefficient can be computed by the original coefficient and then followed by a normalization. So it doesn't change the ratio between the superposition coefficient, but only rescale the superposition coefficient by an overall normalization factor. So essentially that means you are projecting the original state psi into a new state psi prime, which is basically the projection of the previous one into the subspace spanned by these degenerate eigenvectors. Okay, so that's what we talked about last time. Hopefully these steps are clear. And then you can just follow this step. Step number 1, number 2, number 3, and then calculate. Two important things we want to calculate. One is what's the probability and what is the post-measurement state, what's the posterior state after the measurement, right? So that's what we want to compute. And then with this knowledge, I think you can try to do homework 4. We will give homework 4 today. So homework 4 is about a 3-state system where it has 3 basis states, 1, 2, 3. And then suppose the system was originally prepared in a prior state, which is an equal weight superposition of all the 3 basis states, 1 over square root 3 and sum over them. So now we are going to measure an interesting observable, which is written in this form. And you can actually check this is a Hermitian operator, so everything is legal. And then the first question is about what are the possible measurement outcome? And we know the possible measurement outcome are the eigenvalue of this operator. And in order to find the eigenvalue, you first need to represent this operator as a matrix, right? So you need to use this technique of translating all these ket and bra vectors eigenvector expressions into a matrix. And once you rewrite it into a matrix, you can find its eigenvalue and eigenvectors. Both are very important. With knowledge about eigenvalues and eigenvectors, you can try to compute what's the overlap of eigenvectors with this original state, such that you can compute what's the probability for each outcome. Okay? But I need to remind you that this homework is designed in such a way that this observable has degenerate eigenstates, meaning that there are actually more than one eigenvector correspond to the same eigenvalue. So you have to use what we have learned so far to deal with the degeneracy. And then after the measurement, what's the posterior states, right? So just make a table, like if I observe certain eigenvalue, what's the posterior state? If I observe the other eigenvalue, just list all the eigenvalue as measurement outcomes and list all the posterior state correspond to that measurement outcome, okay? So that's the homework 4. Any questions? Okay, so the homework 4 is providing you opportunity to exercise this, technique of calculating probability and posterior states. Okay, so with all this knowledge, now we can talk about another thing, which is the expectation value. Since in quantum mechanics, when we do a measurement, it's all probabilistic, and then if you observe something, the outcome comes with probability. So we can try to calculate certain statistics of our measurement outcome, meaning that you can repeat this experiment many, many times. Then you will observe, you prepare the same state, you make the same measurement, but even if the initial condition is the same, what you do is the same, the outcomes still can be different. That's the nature of quantum mechanics. So every time you do the same experiment, you get a different outcome, but you can do many of the experiments and then try to figure out what's the statistics. So that's the idea. For example, if I measure observable O, and then I want to denote it, I want to understand its expectation value. Expectation value means the average value of the measurement outcome, the mean of the average outcome, which is always denoted as O with this bracket. And then this is the expectation value of this operator. Then what's the definition of expectation value? The definition is, so first of all, you enumerate all the possible observation values. This is a possible measurement outcome, OK, which correspond to the eigenvalue of this O operator, and then it's labeled by integer index k. This k labels different eigenvalues. And then for each eigenvalue, there's a corresponding eigenstate, and then you can compute its overlap with your original state that you start with, and then this gives you the probability. So you have this probability to observe this eigenvalue, this measurement outcome, on that state. And then if you weight the measurement outcome by the probability and sum over all the possibilities, then if you go through this derivation, you will find that eventually it becomes an equation like that, where this inside this part with a summation k, this is nothing but the operator O itself. So this basically tells us the expectation value of this observable is basically taking the corresponding Hermitian operator that represents this observable, which is a matrix, and then take the ket vector, which represents your initial states, which is a vector, column vector. This bra version is a row vector. So you do a row vector, matrix, column vector, kind of matrix multiplication, and the result is a scalar. The result is a number. And that number is nothing but the expectation value. So that's how you compute the expectation value of an observable on a given state. Okay? So first of all, you can actually ensure that this answer is a real scalar. How do I know that? Because if I try to make a complex conjugate of this number that correspond to complex conjugate this expression. But complex conjugate this expression simply means you need to exchange bra and ket and take a Hermitian conjugate on the operator. But since this observable always correspond to Hermitian operator, so its Hermitian conjugate, operator's Hermitian conjugate is the same. But if you exchange ket and bra, there's nothing going to be different. It's the same state on the ket and bra. So that's why the result is always a real number, because this result's complex conjugation is the same as the result itself. So if a number is the same as its complex conjugate, then we conclude that the number must be a real number. And then you can actually write down this expression more explicitly, as I said, in terms of these matrix representations. And it's always good to write in this way that facilitates computation. Alternatively, there's another way to write expectation value as the trace of the product of the observable operator and the state projection operator. So this is the projection operator of the state, which means you are moving this row vector to this side. So once you move this row vector to this side, this column and the row vector multiplied together will give you another matrix. This will be another matrix. So now you have a matrix. This will be a matrix. This is a matrix. This is a matrix. So if two matrices multiply together, the resulting thing is still a matrix. Now I want to get a scalar on the other side. What I need to do is I take the trace. Trace is like summing over the diagonal of the matrix. But the reason this seems to be a simple rewriting because we know trace has nice properties that you are allowed to permute things inside the trace. I mean cyclic permute. So you can permute this side to here, and then this basically simplified to the previous kind of expression. So it seems that it's just a mathematical game to rewrite things like that, but it's actually not. There is a difference. By writing things as a trace of an operator and projection operator, it can greatly simplify the computation. So that's what I want to give you as homework 5. I'm very sorry for that, that I give you 2 homework today. But yeah, take your time to do that. So you can try it. You can use 2 different ways secretly and use different ways to compute things. If you use the first approach, then you really need to know what's the cat vector, what's the vector. You need to find these eigenvector, find these state vectors. Sometimes the state vector is much difficult to find than the projection operator, as we mentioned previously in the Pauli matrix. So homework 5 is indeed giving you an opportunity to see that. So it is about M and N are 2 3-component real vectors. So each one of them is a 3-component real vector. They are just used to parameterize certain generic Pauli operators. So Pauli operators are sigma x, sigma y, sigma z. You can combine them with unit vectors. So that becomes a Pauli operator pointing along the corresponding directions. So now if we consider measuring an observable, which is n dot sigma, and n dot sigma is a 2x2 matrix, on the m dot sigma equals +1 state, what does that mean? M dot sigma is another matrix, and +1 means the corresponding eigenvector of this matrix with eigenvalue +1, okay? So that's a vector, and then that's a matrix. You can try to compute what's the, for example, you can compute many things. What's the probability to observe this n dot sigma? What's the expectation value of n dot sigma on that state, right? The probability was also calculated on that state. But if you use this vector approach, you will find it's really difficult to compute this state vector. It's very tedious. But the state vector itself, although it's difficult to calculate, the state vector cat and bra, when they combine into a projection operator, you can scroll up the lecture notes, and then you can find answers there. The projection operator is very easy. The projection operator corresponds to this one is identity operator plus m dot sigma divided by 2, and that's it. So you don't need to write down any matrix or vector representation. You don't need to write down these things component-wise. You can completely do everything on the algebraic level because we already know if you Pauli operator 2 of them multiply together, for example, sigma x multiply sigma y is I sigma z, right? So you can just use these high-level algebraic rules of Pauli operators and multiply them together, eventually take a trace. Trace of any Pauli operator will be 0, but trace of identity operator will be 2, actually, in this case. So using all this knowledge, I think it's actually easy to do homework 5. But if you don't use this trace technique, you will have a hard time. So this homework 5 is providing you an opportunity, first of all, to exercise the concept of calculating probabilities and expectation values of observables, but also teaching you a trick of how to do that efficiently using this trace operation. Okay, any questions? Okay, so with this understanding of expectation value, let's try to go to the next order. So when you have a bunch of random variables, sometimes you not only want to know what's the mean value, right? You also want to know how much this random observable is fluctuating surrounding its mean value. So that fluctuation, the amount of uncertainty, is captured by the variance. So in statistics, variance is defined in this way, that if you have a random observable or random variable, and then you subtract the mean from the variable such that you obtain the deviation. And then you can square the deviation, because if you just compute the deviation and then average the deviation immediately, it will be 0, right? Because the observable will just fluctuate surrounding its mean. So you need to square the deviation such that it captures the strength of the deviation in some sense, and then you take the average of that. So it's a double average, and since it's a double average, you first need to average the observable inside, and then you average this deviation square outside. And you can expand things and follow the statistics. You can show that it actually has a simpler equation, which is first compute O square average and then minus O average square. It's like that. So this O square average is simply taking this observable and then really square it. Square it meaning that you take the Hermitian operator corresponding to that observable, which is a matrix. Matrix can be squared in the sense that you can take the matrix, make another copy, and matrix multiply with itself is this squared. Okay, so this is the way to compute or to define this O square expectation value. This is the way previously we just learned to define O expectation value. If you take this one minus this one squared, that gives you the variance of this observable. And then we can also define standard deviation as a square root of the variance, because variance kind of measures the square deviation. So if you really want the amplitude of the deviation, it's more like a square root of the variance. Okay, so with that understanding, people can actually derive some very useful relation, which is called uncertainty relation, which is a very fundamental rules in quantum mechanics, which is also a very big difference between quantum and classical. In classical, any observable can be simultaneously measured to arbitrary accuracy, but in quantum mechanics, that's no longer the case. For any pair of observables A and B measured in any given state repeatedly, then you can collect the statistics and you can try to find what's the standard deviation of A and the standard deviation of B. And then this theorem tells you that the standard deviation of these two observables multiplied together will always be greater equal than the commutator's expectation value on the state with an absolute value and 1/2 factor in the front. So this is called uncertainty relation. What does this relation tells us? That means if A and B are two observables, and then you make many measurements, every time you make a measurement, you will collect a point, because when you measure A and maybe also measure B, you collect some points. They actually forms a cloud, and then this uncertainty basically says that what's the region of this probability distribution of the value of A and B? What's the area of this cloud? Essentially, it's quantifying that. And then it's an inequality saying that sometimes it is impossible to make to squeeze this probability cloud to 0 volume. So that's the idea. So in words, this means that the product of the uncertainty cannot be smaller than half of the magnitude of expectation value of the commutator. If for commuting observables, it's possible. For commuting observable, meaning that if A and B already commute, then this operator is simply 0. So 0 operator expectation value on any states will also be 0. So on the right-hand side, it's 0. Then that means there's no lower bound. This uncertainty it is possible to achieve a state where all these observable, both of the observable has 0 uncertainty. That means A and B can be jointly measured with perfect certainty in that case. But if it is a non-commuting observable, that means this commutator is not vanishing for some states, then on that particular state, it is impossible to have this standard deviation both being 0, because that will violate the uncertainty relation. One important scenario is if you think about position and momentum, we haven't talked about that, but it actually has an uncertainty relation because position operator and momentum operator has a non-trivial commutator, which on the right-hand side basically becomes 1/2. Oh, I should say I already ignored some of this H-bar thing, so it's, yeah. Anyway, any questions? Yeah, I just briefly mentioned this because I guess you have already learned some of this in the previous lectures, but I just want to put all this in the context of observables and measurements, okay? So far we have learned the following things. First of all, observable in quantum mechanics is represented by Hermitian operators, and then based on the observable, you can find its eigenvalue, eigenstates. Eigenvalues are the possible measurement outcomes, and eigenstate helps you to compute the probability and post-measurement states. Based on this knowledge, we can compute the expectation value of observables and also the variance and standard deviation and even higher statistics. All of them is well defined. So quantum mechanics is not about trying to predict the observation precisely. It's trying to give you a prediction about the probability distribution of the observables, or it's trying to give you a prediction about what's the expectation value, what's the standard deviation, and what's the higher order statistics about the random measurement outcomes. So unfortunately, our universe, our underlying world is random, and we have to live with that. And then quantum mechanics provides us the mathematical formulation to characterize this randomness. Okay, so that's what we learned about observation and measurement. And then the last topic we want to touch in the first part is dynamics. As we mentioned at the very beginning, quantum mechanics as a physics theory need to provide prediction powers. Prediction powers includes predicting observables, which we already talked about, and also predicting the time evolution, which is dynamics. So when we talk about observables, we talk about Hermitian operator, and when we talk about time evolution, dynamics, and things like that, we have to touch the unitary operator. So let me first introduce what is a unitary operator. Unitary operator is closely related to basis transformations. So we have been talking about basis. That means you can choose a set of orthonormal bases in the Hilbert space to represent either your state or your observables. So suppose we have two sets of orthonormal bases in the same Hilbert space. Which means actually you can rewrite one basis in terms of the linear combination of the other basis. But anyway, these are the two different choices of the basis. That just means that if you are given a two-dimensional space, there are multiple ways of choosing coordinate systems. If you choose the coordinate system in this way, these are your two basis states. You can also, I don't have a different color, you can also choose the coordinate system the other way. This is another, for example, another basis. So this will be my 1 prime, will be my 2 prime, and this will be my 1 and my 2. So I can label my basis state by 1 and 2 cat, or 1 prime and 2 prime cat. They form different bases. That's the idea. The picture is like that. But now if you have a vector, suppose you have a vector like that over there, this is a vector, and you want to ask, how do I represent this vector in this coordinate system? Of course, it depends on your choice of coordinate system. If you represent the vector in this solid coordinate system, it may have a smaller first component than the second component. But if you represent it in this tilted dashed line coordinate system, it has a larger first component than the second component, right? So the components of a vector in the coordinate system depends not only on the vector. The same vector can have different components in different systems. So the vector component is given by the scalar product of the vector, a cat vector, with the broad version of your basis vectors. Okay. So this is in one basis. This is in the other basis. And also, the same operator as a matrix can be represented differently in different bases. So if you want to know what's the matrix component, then this Oij basically corresponds to the ith row and jth column of this matrix that correspond to this operator. And then this operator's matrix representation, again, is this scalar product. You can see it can have different expressions, even if you have the same operator. But now what we want to ask is, how do I relate these two components, right? If I know what is the component or what is the representation of this vector in one basis, and if I also know what's the relationship between these two bases, can I directly infer what should be the vector component in the other basis? The answer is yes. What all you need to do is called the basis transformation. Basis transformation allows you to carry your knowledge in one basis to another basis. And the basis transformation is always implemented by a matrix which is called, which is a unitary matrix actually. And this basis transformation matrix is defined in this way. So this matrix basically describes the relationship between these two bases. You can see this matrix, i's column and the j's row simply characterize the inner product, the scalar product between the i's vector in the prime basis and the j's vector in the no prime basis. So if you have the information about the two bases, the two set of basis vectors, you can calculate what's the interrelationship between each one of the basis vectors from these two sets. And that forms a table or forms a matrix, which is this Uij. And then you can immediately use this Uij to convert the vector component from one basis to the other basis. So if you know what's the vector component in one basis, you multiply this with this U, and then it becomes new vectors whose component is already written in the other basis. These two vectors should be thought as representing the same state, but just representing in different bases so they can look different. How do we derive that? Well, it's very easy. You start from the definition. So Vi prime, you can see on this side, Vi prime. If you follow the definition, it's like the I prime, and then scalar product with V. But then there's a trick. You can insert an identity operator inside this expression, but identity operator can do the magic because you can have a representation, this resolution of identity. So you can resolve it, resolve the identity as a summing over the basis vector on the other basis, and then sum over these projection operators. So now this part becomes Uij, and then this part becomes Vj, basically, okay? So that's just a two-line derivation to show that. You can also try the same derivation for the, for the operator version, for this matrix version. I'm not going to do that. If you don't know how to do that, take a look at the exercise 18, okay? So this is the basis transformation that connects your vector from the original basis to the new basis, and also transform the operators correspondingly. And you can see this is a matrix because it has two indices. But we know that in quantum mechanics, every matrix is an operator. Every operator is a matrix. Whenever you see a matrix, you should think about what's the underlying operator. So whenever you see this matrix element, you can try to use this matrix element to build an operator, and then the operator corresponds to this U hat. So U hat is the abstract operator behind this basis transformation. And what this operator tells us is basically go and find any ith basis state in the prime basis, and then transform that into the ith basis in the no prime basis, right? So you are going from one coordinate system to another coordinate system. What you need to do is you go to find every prime, for example, transform from this dash to this solid. Go to find 1 prime and transform it, bring it to 1. And find 2 prime and bring it to 2. So by doing that, you can rotate the coordinate system to the new system, right? So this is indeed what this operator is trying to do, because we say that when the operator is a summation of this basis operator, this basis operator basically perform a basis change that change you from this basis state to the new basis state, okay? And then you need to sum over all the possible basis states in the set of bases. That's it. So it's very intuitive that this operator actually describes basis transformation. And this operator is an example of unitary operator. And it's actually stronger. Any unitary operator can be understood as a basis transformation, actually. So this is a very concrete example of what unitary operator looks like, and but it's not a very high-level definition, okay? So at very high level, unitary operator is called unitary if it satisfies this property. A unitary operator multiply with its Hermitian conjugate, or the other way around, is always identity. Another way of saying that is that if U is a unitary operator, its Hermitian conjugate is simply its inverse. You can take the matrix to the other side. It becomes the inverse, okay? So remember, for a Hermitian operator, if H is a Hermitian operator, its Hermitian conjugate is itself. So you can see both Hermitian operator and unitary operator are defined by Hermitian conjugate. One is Hermitian conjugate is itself, the other is Hermitian conjugate is its inverse. So if you think about complex number, if you have a complex number, its Hermitian conjugate is like taking a star equals itself. What can we conclude? We can conclude that this is like a real number, right? Then what about for unitary? If you have a complex number, its complex conjugate is its inverse. What can we conclude? We can conclude that its norm is 1, right? So that means this complex number, it's a real part, and then the imaginary part, and then it lives on the circle, unit circle. So that's why we have this name unitary, because unitary operator's eigenvalue or unitary operator is like a complex number on the unit circle. So that's why it's unitary. And actually, it's all its eigenvalue on the unit circle. That's what I want to talk about here. Yeah. Okay, so there's a special case when I and I prime are two sets of identical bases, then you can show that this U, because U is a, remember, U is a summation, summation of I and I prime. If I prime turns out to be I, they are the same basis states, then this becomes the resolution of identity, then the unitary operator becomes identity operator, which is so reasonable, because if I and I prime are identical, meaning that these two coordinate systems coincide, then the coordinate transformation will be a do-nothing transformation, because there's really nothing to do. If the coordinate system already coincide, then you don't need to transform anything. So that's why when the two coordinate system is the same, the two basis choice is the same, the basis transformation between them will become the identity operator. And using the operator, we can perform basis transformations. We can perform basis transformation for cat state, which goes like this, for bra state, which goes like that, for operator, which goes like that. These are just another rewriting of what we have derived previously about how to transform the component, right? Previously, we show how each component gets transformed, but this is just another way of writing those formula at the operator and cat state or bra state level. Okay, I guess this can be understood, because if the cat state is transformed in this way, then the bra state should be transformed correspondingly. But correspondingly by what? By taking a Hermitian conjugate on both sides, right? So taking Hermitian conjugate on this side brings cat to bra. On that side, you need to take U to U dagger. And then because O as an operator is made of a cat and bra state, O can be written always as a cat and bra outer product and superposition of that. So if every cat and bra state is transformed in this way, then O must be transformed as U, O, U dagger, because O has a cat state on the left and the bra state on the right. So that's why when you transform a matrix or transform an operator, the unitary matrix need to come from both sides, and then the unitary are basically U and U dagger from both sides. And if the operator and states are transformed in this way, you can show that one thing is invariant under the basis transformation. That is the expectation value. Expectation value is given by this scalar product. But if this cat state transformed to U times the cat state, the bra state transformed to bra state times U dagger, and the operator transformed to U, O, U dagger, you can show that U dagger and U come together and becomes identity operator. So nothing is changing. So this expectation value is unchanged. So what does that tell us? That tells us the basis choice is a human choice, right? It's just your choice of how to represent this state and observables. What the nature can see is only the expectation value. If you go and measure a quantum system, you can only measure its expectation value, measure its variance, measure its standard deviation. I didn't talk about the higher order statistics, but actually following the same principle, you can show that to all order, expectation value, standard deviation, they are all not going to change if you perform basis transformation. So basis transformation has no effect, no physical effect, and it's just a choice of language. That's why in quantum mechanics, we are so careful about separating state from observables. In classical mechanics, you use the same language to describe state and observable. For example, if I'm standing here, my observable is like my momentum is 0, but that's observable actually. But you also use momentum being 0 to describe the motion of the state of motion for me in classical mechanics. But that's no longer true in quantum mechanics because the description of the state has a lot of ambiguities. For example, basis choice is ambiguities. So that's why quantum mechanics use a much more redundant language to describe our states. And we have to do that, unfortunately, because observable don't commute with each other. That means you cannot just use observable to describe the state. That will be incomplete. So you have to use this redundant language, but then you have to deal with this basis choice. So all the physical quantities.
Sorry, quick question, just to make sure. So the reason why we know that physical reality should be basis independent really comes down to the fact that all of the moments, like the expectation and all of the moments, are basis independent. And so because the moments and if we know all of the moments and all of that, then we know the distribution, right? Yeah.
And the distribution is also basis independent because this. Distribution is always given by scalar product. And then if you insert U and U dagger, it's also not changing. Yeah. Yeah. Any questions? Okay, so that's all I want to talk about this unitary, and that's an introduction of unitary operator and basis transformation. And why do we need to do basis transformation? Because sometimes you may be writing down your operator in an unsuitable basis, but sometimes if you bring it to a new basis, it will simplify the calculation. So for example, if you have let's say you have a Hermitian operator, you can always do something called matrix diagonalization. We have already been talking about this many, many times. But with this new language of unitary operator, today we will have a little bit higher understanding that the nature of diagonalizing a Hermitian operator, previously we say it's like finding its eigenvalue and eigenstate. That's true. But actually, it's also finding a unitary operator to bring the Hermitian operator to its diagonal form by transforming to its eigenbasis. So you want to transform something to the eigenbasis, then that basically corresponds to such a unitary transformation. This OK is the eigenbra of this operator, and then the case eigenbra of this operator. And this k just simply means a one-hot vector with the case component being 1. And then this eigenbra may not be a one-hot vector. It may be a very complicated eigenvector. Who knows, right? So by saying that I want to bring it to the eigenbasis, meaning that I want to get rid of this very complicated eigenvector and then replace it by a one-hot vector which only has a single 1 in the case component. So in that way, if you perform this unitary on the operator, you will show that this matrix multiply that matrix multiply this matrix dagger will give you a new operator where the new operator on the new, it's actually, in terms of operator, it's the same operator. It's just a new representation of the operator in terms of matrix. It will become a lambda, which I denoted as lambda, which will look like a diagonal form, basically. So the diagonal matrix element will just be the eigenvalue of this O operator. So you can always think that what happens in matrix diagonalization is to find these unitary to bring the operator to diagonal. But this unitary can be simply found by computing basically the eigenvectors. So once you find the eigenvector, you just put all the eigenvector in different rows. Put the first eigenvector, the broad version of the first eigenvector in the first row, and the second eigenvector in the second row. If you pile them together, and then that will be your U matrix. So that U matrix is just simply constructed from eigenvectors. And another way of saying this is every Hermitian matrix can be written in this way. That's just another, you just inverse all these matrix to the other side, such that because we know the inverse of unitary matrix is just Hermitian conjugate. Of course, Hermitian conjugate is much simpler to compute than the inverse, right? So unitary operator has this nice property that its inverse just requires a Hermitian conjugate. And then every O can be written as a diagonal matrix transformed by the unitary. And then that's another way of saying it. Yeah. Okay, so I think I'm just, we can just look at the example. For example, if we have a Pauli matrix sigma x, let me remind you that sigma x looks like this, looks like this. So this matrix is not diagonal, and then we want to find a unitary operator, or unitary matrix to diagonalize it. And here is the answer. What you need to do is to put the two eigenstates, which is plus and minus. If you scroll up the lecture notes, you will see what's the corresponding eigenstate of this matrix, which is 1, 1 and 1 minus 1, divided by square root 2. And this unitary actually has a name in quantum information called Hadamard gate, which is a very important single qubit gate. The reason that it's important is because if you apply this unitary transformation to this sigma x operator, which correspond to this matrix, multiply that matrix, multiply this. This is U, this is X, this is U dagger. And then you will once you finish this computation, you will amazingly found that the matrix becomes diagonal. First of all, this is not diagonal, but it gets transformed to a diagonal matrix. And the diagonal matrix elements simply correspond to the eigenvalue we just put in. And then this diagonal matrix corresponds to sigma z. So this is a very important operation which allows us to transform sigma x to sigma z. But why that is important in quantum information processing? Because sometimes we want to measure sigma x, but actually there's no way to measure sigma x directly. On a quantum device, the only thing you can measure is sigma z. Sigma z is the only observable you can directly measure. So what people do is that before I want to measure sigma x, I first perform a Hadamard gate that transforms my basis to the z basis. Then I perform a z basis measurement, but the measurement outcome actually tells me about sigma x observable before the unitary transformation. So, so that's how people do these quantum measurements on quantum devices. Okay, I guess any questions at this point? Yeah.
You mentioned that you can convert from sigma x to sigma z. Is there any use of sigma y in this, or is that just like any corollary to like the Hadamard gate that like converts from sigma z to sigma y? Is there like a benefit to using sigma y in any cases?
Yeah. So we also care about sigma y. So there's another gate which converts, which is the Hadamard gate followed by a phase gate, which converts sigma y to sigma z. And then if you want to convert sigma z back to sigma x, what do you need to do? Yeah. That's okay. That's very good. So if you want to convert sigma y to sigma z, again, you just you construct similar things, but here you use the y eigenvectors, which goes like 1i and then 1 minus I, like that. Okay. Yeah. Okay. So any further questions? Yeah, if not, let me talk about the relation between Hermitian and unitary. You can see Hermitian and unitary looks somewhat related. They all has to do with Hermitian conjugate. There's a very profound relation between these two types of operator that if Hermitian operator are generalization, you can think of it as a matrix generalization of real numbers, as I said that, then unitary operators is like a generalization of phase factors, which is like that. So in complex numbers, if we don't consider matrix, just fall back to complex numbers. So if you have a z as a complex number, if the norm of z is 1, then any phase factor can be written as e to the I theta, where theta is a real phase angle. So that's what we learned previously. And then, so that basically reveals a very profound relation between real number and the phase factor, right? Z is a unitary complex number, meaning that the norm of z is 1. The norm of z is 1, then z must be able to be written as e to the I, a real number. Real number is like Hermitian operator. So that's the same idea. The idea is that every unitary complex number can be written as e to the I real number, right? Or any real number, if you raise it to the exponent with an I in the front, then it gives you a unitary or a norm 1 complex number. So it's both ways. So the simple idea also apply for operators. Every unitary operator can be generated by a Hermitian operator in the form of e to the I theta, where theta is my Hermitian operator here. And then every Hermitian operator, if you raise it to the exponent, that generates a unitary operator. So this is both ways. There's a relation. But I need to emphasize, what does it mean by this exponential? We have talked about exponential map of operators, right? It is an operator function. It is not taking the exponent of every component independently. Don't do that. Don't do matrix element-wise exponentiation. You need to really exponentiate the full matrix, meaning that you need to Taylor expand this exponential formula and then do the matrix multiplication and then sum them together, and then that's the new matrix, okay? Of course, that's not very simple, but there are ways to understand that. First of all, if theta is a Hermitian operator, you can always do spectral decomposition in terms of eigenvectors and corresponding eigenvalue. Then, given that knowledge, e to the I theta can either be, this is the definition, either you just follow the definition and calculate all these complicated things, or if you know the spectral decomposition, you can immediately use the spectral decomposition. I think that's not. I think we touched that in homework too. We can prove that this basically you can reconstruct this unitary matrix by taking the every eigenvalue, raise it to the exponent, and then reconstruct the unitary matrix from that using this information of eigenvector. You don't need to solve for the eigenvector again. You just need to diagonalize it once. Once you know the eigenvector, you can use the eigenvector and the exponentiated eigenvalue to reconstruct unitaries, okay? So following that, basically, I just want to finish this example in 2 minutes. The unitary can, for example, we can consider a Pauli matrix, which is sigma y. Actually, we have talked about that in exercise 10. You can show that e to the I theta sigma y actually is a matrix like that. So this is actually a unitary matrix because if you try to Hermitian conjugate this matrix, you can show that it's on inverse. The Hermitian conjugate is its inverse. So it's unitary. So this unitary basically implements a basis rotation of theta by theta rotation angle. So this unitary is the unitary that performs the basis rotation in this two-dimensional real plane. So if you want to rotate the whole coordinate system by an angle theta, the unitary transformation you need to do is this cosine and sine thing, because you can see it transforms a vector along the x direction to a new vector along the theta direction. So in the special case, when theta equals 0, this becomes identity matrix, and no rotation is performed. So that tells you how to use a Hermitian operator followed by the exponential map to generate a rotation or a unitary operator. Okay, so that's the general principle. And that's it for today. Thank you.